Okay, so let's start. So what did we cover in the last session? We covered binary search trees and balanced search trees, right? And what's the major difference between binary search trees and balanced search trees? It's in the complexities, right? In the worst case, binary search trees take n time for insert, search, and delete in the worst case, right? A best case, say, search can be one time also, right? But in the worst case, it is n time. On the other hand, balanced search trees have the complexity of O of log n for insert, delete, and search. And so another beauty of these trees is that when we take the in-order traversal of these trees, right? In-order traversal. And what do we get? The sorted order. We get all the elements in the sorted order. So that's beautiful, right? So it's not just for inserting, deleting, and searching, but it is also for sorting. So one simple idea is, see, here is a sorting algorithm. Insert items one by one to, say, balanced search tree, right? What do you get? The first insert takes log n time. I mean, say, right, it's one, but say log n, right? The second item in the worst case takes log n time, so on. So if you keep adding n items into a balanced search tree, what is the total cost? Worst case cost, n times log n and log n. So you can use this data structure as a sorting algorithm also, right? If you keep inserting them and take the in-order traversal, what do you get? The sorted order. So this is called tree sort, right? This is an algorithm called tree sort. The idea is very trivial, right? Keep inserting items one by one into an order tree like this. And as each operation takes log n time, the complexity is n log n. So this is another good sorting algorithm. We use the data structure to build a sorting algorithm. So the constructing the data structure itself is complicated. But once we have it, it is trivial to get the sorting algorithm, right? N log n. So see, that's why this is a very powerful data structure, trees, right? Okay, and we were looking into cache efficient data structures. The computation wise, it is fantastic, right? It's just mind blowing. That's okay. What about communication? We said that these are great data structures computation wise. They are computation efficient, but they are not communication efficient. And I also give an example, right? Accessing anything in your hard disk takes a lot of time, maybe a couple of milliseconds. So in which case you could have done maybe 1,000 or more number of multiplications. So communication is expensive. So you want to reduce communication, that is message transfers, right? Page faults in operating system terminology. So we want to develop cache efficient algorithms. Okay, so there are two features you need to think of when you want to come up with cache efficient data structures or algorithms. Spatial data locality, temporal data locality. So what is spatial data locality? So let's read the meaning of this, right? This sentence, then we will analyze this. Whenever a cache block is brought into the cache, it contains as much useful data as possible. So what is the meaning of this? Think about a library, right? So think about a library. So you have a collection of books here. And so suppose you are sitting here near a table and you have all these books that you want to read. Now, suppose you want to bring in a couple of books for your study. What is the best way to do? So when you go here, try to collect books, right? That you will be reading before again moving to the library or the building and keeping them. So when is that easy? When all the relevant books are together, right? Suppose these are all, say, mathematical puzzle books. If they are together, you can collect them and bring it to the table. And once you have read them or once you're bored, you can keep them back. Communication is just, say one round trip. But suppose they were here, 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 right? Then what do you need to do? So you will need to travel a lot, right? So that is not communication efficient. So from these simple examples, you can see we can exploit these ideas in algorithms also. Whenever a cache block is brought into the cache, it contains as much useful data as possible. So try to bring in the books. So even if they are here, right? So try to bring in the books so that you can so that they are all related to each other and you can read them together and keep them back, right? So even in that case, you are reducing communication. That is spatial data locality. So what about temporal data locality? Whenever a cache block is brought into the cache, as much useful work as possible is performed on this data before removing the block from the cache. So what is the meaning of this? Spatial locality is related to space. Temporal data locality is related to time. So that means whenever you bring books to the table, make sure you read as much as possible from those books before keeping them. Why? I mean, what if you read one paragraph, keep the book, again, get another book, read one paragraph and get the original book again? I mean, it doesn't make sense, right? So you want to make use of the book as much as possible before you hit or collect that book again and again and again. So this is related to time, right? As much useful work as possible is performed. So this is related to time. I mean, so try to get as much work from the book point of view, try to exploit it as much as possible, right? So that's the idea. Okay. So if you want to have temporal data locality, so there is one necessary condition. The necessary condition is that, look at this, the total number of computations should be asymptotically greater than the space complexity. Asymptotically greater. I mean, why is this a constraint? Think about it. Suppose you are doing, say, 10 computations and the space itself is 10, right? The space is 10. Then you cannot do a lot of work. I mean, what is the ratio? Ratio is something like constant here, right? That means one computation per space or spatial cell. Per spatial cell. I mean, you cannot reuse. I mean, once you have brought that variable or value, whatever, you cannot reuse. You can only perform one computation and then you have to throw that value away, right? So you cannot reuse computation. But if this is, say, 100, what probably, so this shows that if it is asymptotically greater. So here I'm just showing you an example, but here this is related to asymptotics. Okay, so so you can probably perform 10 computations whenever you bring one spatial cell. That's the idea here. Whenever you bring, say, one variable or one cell from a DP table or whatever, you can perform 10 computations. That means you're reusing, right? And doing a lot of computations on that space that you have brought into the cache before evicting that out, right? So that's the idea. So if T of n is asymptotically greater than S of n, maybe for like whatever you bring in the space, right? The space is the cache block and cache block is the data. right? For that data, you can perform a lot of computations before throwing that off. So similarly, I mean, in the library scenario, when you bring in a book, make sure you read as much as possible in the book, not just one or two lines. I mean, one paragraph or two lines, right? As much as possible. So that's the idea here. A lot of computations per space. So this is the necessary condition. If they are equal, no, you cannot come up with a cache efficient algorithm, right, for that setting. You need to think about a way to reduce space further, and so that there is a gap between computation and space, right? And then try to come up with cache efficient algorithms. Okay, and what is the best approach to come up with cache efficient algorithms? Recursive divide and conquer algorithms, right? Try to design these, and in most cases, they are cache efficient.
Professor,
yes.
What does omega mean here?
Omega. So what is omega? So we covered this in analysis of algorithms, right? Asymptotically greater.
Okay.
It is strictly greater than S of n.
Okay.
Right? Strictly greater. We had another notation, right? What is the notation we used? Something like this.
Yes, we did. Yeah.
Right? So we need to use this notation.
Okay.
So this is one of my research areas, cache efficient algorithms. And how do we proceed there? Again, we design recursive divide and conquer algorithms. So when we work on that, we work on dynamic programming algorithms a lot. And what do? We develop cache efficient dynamic programming algorithms. That means we develop recursive divide and conquer algorithms on top of DP. You might have heard about DP. We apply recursive divide and conquer algorithms on these DP algorithms, right? So that makes it cache efficient, right? Okay. So anyway, let's proceed. Then we need to define a metric called cache complexity. What is cache complexity? The total number of cache misses or page faults, or you can say message transfers or block transfers between adjacent levels of memory. That's cache complexity. So you have heard about total number of computations, you have heard about extra space, you have heard about total space. Now, I think for the first time, we are seeing another metric, right, of comparing algorithms, cache complexity. So this is related to communication, right? How much communication the algorithm uses. See, now think about this. This is your hard disk, this is your RAM. And whenever you even read a variable, right? What happens is only that variable will not be brought into RAM. The entire block of memory, so this might be say 64 KB, right? It totally depends on operating system and the computer itself, right, that you're using. So it might be 64 KB, it might be 512 KB, it might be 4 KB, whatever, right? So that's a block size. And the block size differs with every two adjacent levels. The block size is different between L3 and RAM, L2 cache and L3 cache, so on, right? The farther you go here, the block size increases. So this might be say 64 KB or 4 KB. I don't know. You need to check it. It is dependent on operating system, machines, and everything. Anyway, so any algorithm will transfer data from between different levels of cache or memory. So the total number of these block transfers between adjacent levels of memory is called cache complexity. And what is a cache efficient algorithm? You want to minimize these cache misses or block transfers. Okay, so ideally cache efficient algorithms should exploit both spatial locality and temporal locality. And remember all those definitions, right? And here B is the data block size. The size of this is B. and the size of RAM is M, right? Or you can think of size of L3 cache is M dash, and the block size here is B dash, something like that. I mean, you can define it between every two adjacent levels. Okay, next. Now let's look at some of the computation efficient but communication inefficient algorithms. For sorting, we know merge sort. Merge sort is solid, beautiful algorithm, right? Computation efficient, but communication inefficient. Balanced tree, we saw 2-4 tree. It is computation efficient, but communication inefficient. Matrix product, I mean, you can write a simple, iterative, right, non-recursive 3-line code for matrix multiplication. So that is okay. It's not the best algorithm in computation, but okay. But it does not exploit communication at all. It does not better communication. What about the communication efficient counterparts? So there is something called M by B way merge sort. I mean, we will not go over this, but just remember it, right? It might be helpful for your interviews or in general, right? Okay. So this external memory merge sort, M by B way merge sort, what it does is, of course, the computation is n log n. Not just that, the communication will be something like this. Total number of data block transfers will be n by b log of n by b base M by B. And you know, capital M is say RAM size, B is block size. And so what about communication of this merge sort? It is same as this, n log n. And you will see that when you implement both of these, the normal merge sort for say 10 GB data might take several hours. On the other hand, external memory merge sort might take just a few minutes or maybe seconds, I don't know, right? Do all these experiments. This is the power of cache efficient algorithms, right? So this will take hours, and the external memory merge sort might run in seconds or minutes. So that's the beauty of cache efficient algorithms. What about balanced trees? There is something called B tree, right? A specialization of 2-4 trees, so which can reduce the communication complexity, right? That is the total number of page faults or cache misses or data block transfers to log n base B. If B is say 64 KB, right? 64K, that's a big number, right? Or if it is, even if it is 4K, 2K, 1K, whatever, it's still a big number, very big base. When the base increases, what happens to complexity? Complexity decreases, right? So this is beautiful. Next.
Sorry, Professor. So here the B tree, the B means that block size?
Block size, right.
Okay.
Capital B is the block size, capital M is the RAM size.
I know, I mean, the B tree, the B itself means that block size.
No. So B, it is not clear, but one of the creators of B tree is Bayer, I think.
Oh, okay, I see. Okay,
right?
it's a
Probably
name after his
might
name. Okay.
be after this person.
Okay.
Okay. Recursive divide and conquer algorithms for matrix product. What is the communication complexity? N cube divided by B root M, right? This is much better. So anyway, so that's the importance of cache efficient data structures as well as algorithms. Now let's look at the straightforward generalization of 2-4 trees. We will call them AB trees. AB, okay? You know the meaning of 2-4 trees, right? The nodes can be 2 node, 3 node, 4 node. What about AB trees? The nodes can be A node, A plus 1 node, A plus 2 node, so on up till B node, right? So that's it. So look at this. AB tree is a multi-way search tree such that each node has between A and B children. That's how we define 2-4 trees, right? Between 2 and 4 children. And the number of keys they had was between 1 and 3. So here it will be between A minus 1 and B minus 1 keys. right? That's your A-B tree. Very simple, straightforward generalization. Okay, so here we need to make sure one of the extra properties are satisfied. So A is greater than or equal to 2, and then less than or equal to B plus 1 by 2. Okay, and the other remaining properties remain the same, right? Size property, depth property, and all that. We have already seen this. The extra property is this. Okay.
Question here, Professor.
Yes.
So here the A does not have to be less than B.
A should be less than or equal to B plus 1 by 2. Why do you say A does not
So
have?
give an extreme example, right?
Uh-huh.
Because I'm sorry, yeah, because B plus
No,
1
A
divided by
should
2.
be
Okay,
less than
okay,
B,
okay,
right? A should
okay.
be less than B.
Got it, got it.
Okay.
One more question, actually. I'm sorry.
Ah.
So here we saw that 2, 4, 3 complexity is log n, right?
Correct.
Why it's not log base 4n, or it doesn't matter?
Yeah, it's a constant, right? We don't.
Yeah, anyway, yes, it is a constant, that's sure. Yeah.
Okay, now let's define B trees. What is a B tree? B tree is one type of AB trees, right? We will see that. Okay, so B tree of order D, look at this. B tree of order D is an AB tree with A is equal to D by 2 and B is equal to D. So if you look at this, A is half of B, right? Half of B, right? A kind of takes the maximum value it can take, that is half of B. Okay, what else? So, and why should this be efficient? Now, what we will do is we will set D is equal to capital B. So what is the meaning of this? Okay, can you tell me what is the meaning of this? You know that this is a data block that travels between RAM and hard disk, right? This is of size B. And what we are saying is that D is equal to B. Okay, so what is D? I mean, this small b is equal to capital B then. What is small b?
That's your maximum children, number of
Maximum children, right? Or you can say that the total number of keys, the total number of keys is B or B minus 1, whatever, right?
Yeah.
So
yeah.
that means the total number of keys will fit into one data block. That means one node will fit into one data block, right? The maximum size of the node is one data block. Why did we do this? Because we wanted to stuff in as much data as possible so that we can make a data block, correct? We wanted to, fully exploit that block, data block. Hence, we stuffed in as much as possible. We kept the number of keys as approximately equal to B. It might be B minus 1, but verify all those, tiny cases, right? And what is the minimum data you can put in a data block?
1, right? Or 0?
No.
Oh, okay.
So
this
here
one. Yeah.
It is B by 2.
Yes.
So any node is at least of size B by 2, isn't it?
Yes.
So any node should have minimum of, say, approximately B by 2 keys and a maximum of B keys. I'm not considering plus or minus 1, okay?
Okay.
Minimum of B by 2 keys and maximum of B keys. I mean, this is the beauty, right? So we are trying to stuff in as much data as possible into, each block, or you can say these are called pages in operating system. This is a page. One page is brought from hard disk to RAM, or RAM to L3, or whatever, page size, right? So node, every node in this tree, it has the size of theta of B, correct? Node size is equal to theta of B, constant times B. So this is where, right, we get that complexity. Now think about it. So how, like, what is the height of this tree? What is the height of this tree? Can you tell me what is the height of this tree?
It's log D, right?
Huh?
Log n base D.
Why is it base?
Base A.
Why is it base B? How did you get log n base B?
So I think it's, you can analog this to binary tree, right?
Yeah. So now think about the branch factor. What is the branch factor of this?
Yeah, yes. Up to B.
Right. It is theta B. If the branch factor is theta B, I mean, everywhere, what does it mean? Right? You are cutting down the tree or data into, divided by B always. Right? So that's why the height of this tree is log n base B. Of course, computation remains the same, right? Computation, there is no change. It is log n base B. But whenever you touch a node, you are loading that node into RAM, right? How many such loads happen? The number, sorry. This is computation, right? This is communication. The number of loads of these nodes is this, log n base B. Computation remains the same, it's log n, right? Because you have to scan all the, even if there are log n base B nodes, the number of keys remains the same, right? I mean, there is no difference in the computation wise. The only difference is how many nodes do you need to load into RAM, and that will be reduced to log n base B. This is how you get cache efficiency. Okay. Now look at this. So I mean, this shows the difference. 243. Communication is log n, computation is log n. B tree, computation is log n, communication is log n base B. Look at the improvement. This is a big improvement. And this is the reason these cache efficient trees, right? Communication efficient data structures, right? Trees, right? And of course, this is balanced, right? Hence the complexity remains the same over search, insert, and delete. So this B tree and its family, typically when we say B tree, it also means it's like entire family, might be B plus trees, B star trees, B hash trees. There are also something called R trees, R plus trees, so on. A lot of tiny variants of this, right? These are used to implement all file systems, right? Whatever file system you see, NTFS, HFS in Microsoft, Mac, Linux, so on, they are implemented using B trees. Oh, when I say B trees, it's a family, right? It can be any of these family. Or think about databases. One is file systems, second is databases. There are databases everywhere, right? Oracle is one of the richest companies out there. And why? Because you need database everywhere, right? You need a database in a hospital, you need a database in a university, you need database in banks, you need databases in government organizations, you need databases everywhere, right? Patient database, employee database, student database, so on. And how are they implemented? They use, again, balanced search trees, right? These B trees or variants of it, or R trees. I mean, there are a lot of variants, but the core idea, whenever we say B trees, the core idea of stuffing, right, all the keys or numbers or these kinds of values into one complete data block or page, right? So whenever we say B tree, the exact number doesn't matter. The concept of stuffing all these values into one data block, right? That's the idea. So all these databases use B trees or these kinds of cache efficient trees. Make sense? The biggest application, right? All these are the biggest applications of trees. Okay, so I think we are done with trees. Do we have any other slides? We are done. And you need to know all the complexities of trees, right? Very important. And this is also a dictionary, but if you need a sorted set, right, then trees are the best. Trees are the best implementations of sorted sets, sorted maps. That sorted is important. If you don't need sorting, suppose you want all these search, insert, delete, but you don't want sorting, you don't care for sorting, then you need hash tables. Okay, so know this very big difference, right? If you want sorting, go with trees. If you don't want sorting, but you still need that insert, delete, and search in a very fast manner, then go for hash tables. This is very important because I have seen students use sets where they could have used hash tables, right? I mean, they did not think about whether ordering is required or not. They just thought about insert, delete, search, and they immediately used trees. Of course, something worked, but that's not the aim, right? One is you want to use the minimum data structure, the smallest, simplest, I mean, that's the keyword, simplest data structure that solves the problem in the most efficient way. Right? So one can use trees, but it's complicated, right? Balanced search trees, a lot of details. If you look at B trees and a lot of details, you don't need them. If you just want an unordered set, right? So you need to be very, very, very careful. Okay. Now let's start with hash functions, right? We'll cover hash tables, hash functions, and so on. Hash tables. And before we start, why do we care for hash tables? This is also a dictionary data structure. I mean, you can say, right? Dictionary data structure, where ordering is unimportant. You don't care for sorting. You don't care for ordering. You just want an unordered set, unordered map. I think in C++, there is a data structure called unordered map, unordered set, something like that. And they must use hash tables, right? Okay, let's start. Hash functions, hash tables will cover collision avoiding techniques, separate chaining, open addressing. We will see how insert, delete, search works in all these things, and we will see one or two applications, right? Okay, let's start with hash functions. See, hash table is the data structure. Okay, so hash function is a concept that is used for these hash tables. Okay, ultimately we want the hash table data structure. For that we are defining hash function. Okay, remember this. Let's start with hash function. What is a hash function? It is a function. It maps arbitrary size data to fixed size data. The input is data, output is data, definitely. But the input data can have any size. It can be, 100 terabyte. Fixed size, that is fixed, right? It can be 10 bytes. It can be 1 KB. Whatever you are given as the, space that, right, that is dependent on the application. If you're using a phone, that's not even a smartphone, right? Very ordinary phone, which is not a smartphone. I mean, think about the space limitations, right? probably you're working with 1 or 2 MB, that's it. But if you have a smartphone, maybe you can increase the space. So that fixed size, you can change the size depending on the application. But the input size, you don't have control over it. It can be anything. Okay, of course, you can give a bound on some of these input data sometimes. See, like whenever you ask for passwords and all, right? You can say, give a password that is not greater than 36 characters. There you are restricting the size of input data. But in general, if you don't restrict, right, it can be arbitrary. That's the idea. Okay, arbitrary input data will be converted into a fixed output data. That's the hash function, right? Hash function converts this. Now let's take a simple example. In cryptography, this is heavily used in cryptography. Hash functions are heavily used in cryptography, right? Cryptographic algorithms. So here it's called digest. So you have a hash function that you use in cryptography. You take anything as the input, right? Any string as the input, and you convert it into a fixed size data. So how many characters do we have here? Maybe 4 times 520, maybe 40 hexadecimal characters, something like that, right? So that's called a digest. Whether you input 1 character, it doesn't matter. The output is 40 characters. Whether you input 1 trillion characters, it does not matter. The output is 40 characters, right? So that's your cryptographic hash function. Okay. Why do we need such a thing? And what are the properties of these hash functions? Let's see them and analyze them one by one. So it should be deterministic and fast. It should be deterministic. That means every time you give the same input, you should get the same output. It shouldn't happen that you give the same input and you are getting 2 different outputs. No, it should be deterministic, means that. And fast, okay, this is obvious, right? Computing message from hash value is infeasible. Okay, so what is the idea here? This is called one-way direction, right? One-way direction. That means you should be able to go from input to output. But it should be easy to go from input to output, but it should be extremely complicated, very, very complicated to go from output to input. You cannot say impossible, right? So everything is possible here, right? It is extremely complicated. Computation-wise, it is extremely complicated to go in the other way. If you're given the output, can you find the input? It should be extremely complicated. Okay, next, computing 2 messages having same hash value is infeasible. So what is the meaning of this? See, the output is a fixed size. That means there will be 2 different inputs that map to the same output, right? Why? It's simple. You're mapping infinite possibilities to finite possibilities. So there should be clashes based on this simple pigeonhole principle. There should be clashes. However, it should be extremely difficult to compute those 2 different input that maps to the same output.
Professor, I have a question.
Yes.
So computing message from hash values. So basically, if you start with the hash, it's going to be really difficult to get your actual, like, the input that you put in. Correct. Is that like if you don't have a key, like, to convert back and forth between, like, if you don't know what algorithm was used to turn the input into the output, you can't inverse that? Or is it just like if you just have the hash?
Both. If you don't know the hash function, also it is difficult. Even if you know the hash function, let me think about it. If you know the hash function also, Yeah, and for simplicity, let's assume that even if you know the, if you don't know the hash function, it is difficult. So it is like this, right? In Apple, they say that if you lose your Apple ID, right, then you cannot get back your ID again. Why? Because they might have the, encrypted version of your ID, but they cannot get back the ID itself.
Yeah, yes, actually, if you don't mind, for the cryptography, even you have the hash, you have the hash function, but you don't have the key, then ideal cryptographic function should be such that it's impossible, basically technically impossible to calculate the reverse order. Or it takes tremendous amount of time, like say 100 years or something like that.
Right.
So,
Yeah, it should be, let's not say impossible, because maybe there is always a way, but it is a slow approach, right? But yeah, very difficult, extremely difficult, right? Something like that. So, okay, next. Tiny change in message must change the hash value drastically. What is the meaning of this? Maybe you input A, you got a digest, right? You got a hash value. If you just add something like this, AB, this hash value will be completely different from the previous hash value. Just a tiny change, right? Or something like this. Now, let's look at this sentence and this sentence. What is the difference?
U and V.
V and U.
Yeah.
But look at the digest here. Everything is different. Right? Something like that. So an ideal hash function should have all these properties. Anyway, let's proceed. There are a lot of applications here. You can go deep into these applications and how exactly hashing is used in all these applications. Let's take a very simple application, password authentication, right? So whenever you have to log in into a website, you get this box, right? Username box and a password box. And then you log in. All these algorithms, websites, they use this hashing algorithm. See, username, you don't need to encrypt or anything. Assume that that's normal. Password will be encrypted. Password will be encrypted. So that means even if you get this database, right? Suppose you hack this database of encrypted passwords. From here to know the password, it will be extremely difficult, right? So suppose you got a copy of this encrypted password, right? Database of encrypted password, and you gave this here. It doesn't matter. When you apply the hashing algorithm, right? The hash of this will be something else. It did not match. So how do you get this? This is the inverse function, right? Suppose this to this is F. This is F inverse. So F is some algorithm they use. It should be very difficult to find F inverse. That's the idea. Okay. Now let's move to hash tables. So what is a hash table? Hash table is a data structure. Okay, it is used to implement a dictionary. So in dictionary, what are the three very basic functions? Insert, delete, search. Simple, right? Okay. Now, hash table is a very good data structure. It's a very efficient data structure to implement unordered, right? By default, these are unordered, right? We discussed all these things in detail. Set, multi-set, map, multi-map. By default, these are unordered. What about ordered set or sorted set, sorted multi-set, sorted multi-map, sorted map? You need to use balanced search trees, not hash table, right? If they are unordered, then you need to use hash tables because they are more efficient than using trees. It's not that trees don't work. I mean, you can use trees also, right? it's not problematic, just that the performance will be bad because you can do better with hashing, right? Okay, next. Hash table performs all these operations in constant expected time. Look at the beauty of this. You could have implemented all these using balanced trees. Then your complexity would be log n, correct? In the worst case. But if you use hash tables, it can be O of 1 in the expected sense, right? Constant expected time. So this is beautiful, right? This is powerful. I mean, worst case can still be bad, but the expected case is constant. That means in most of the runs, it usually runs pretty fast, right? So here is the table that you need to understand really, really well. The three basic operations, balanced trees, they take log n time. Hash tables, expected sense, average case, it is O of 1 time. Worst case can still be O of n, but why do we give less importance to this worst case? Because this happens rarely. So think about quicksort, right? Quicksort is not covered. We'll cover quicksort later. The worst case of quicksort is n squared. But it is called the fastest RAM algorithm. Why? All your programming languages, whenever you call sort, they typically use a variant, either quicksort or a variant of quicksort. Why? Why not merge sort? Merge sort has n log n worst case complexity, but quicksort has n squared worst case complexity, but still they implement quicksort. The reason is that worst case happens kind of rarely, right? Not frequently. Hence, we do not, keep talking about this worst case for hash tables or for quicksort. For some of these algorithms, these worst case happens rarely, right? So if we choose a good enough function here, we typically can avoid this worst case. But it's difficult, right? You need to practically check all that. But hence, we focus more on this expected case, because hashing is a heavily used data structure, right? So we typically use this because worst case happens rarely. Okay, next. But if somebody wants to find the worst case, you need to give this, right? Okay, there are a lot of other operations that you might be interested in. Maybe you want to sort, you want to find the minimum, maximum, predecessor of a value, successor of a value. Maybe you are given a range A to B, right? Find the minimum element present in this range, right? A maximum element present in a range, the sum of all elements that are in the particular range sum. Then balanced trees rock, right? They are amazing data structures for all these. Why? Because all these are related to sorting, right? Minimum. Okay, if you have a sorted set, finding the minimum is finding the leftmost element. Maximum, finding the rightmost element. Predecessor, just going one step to the left, one step to the right? So on. That is easily doable in balanced trees. Of course, you can also do it using hash tables, but they are very bad, right? They have very bad complexity. Okay, so any sorting related operations, go for trees, balanced trees. Any operations that are not related to sorting, unrelated operations, go for hash tables. Okay.
Perfect question.
Yes.
So I think in my mind, it's impossible to do the sort in the hash table if you don't care about the keys, just the hash values, because the hash values are kind of random, right?
No. You can always scan it, right? Hash table is just an array.
Yes.
Scan the entire table, find the minimum. Scan the entire table, find the second minimum. It's a
But-
dumb algorithm, but you
I
can.
know, but it's just find the minimum of the hash, not the key, right? Not the original data.
No. So
Here, when you mean sort, you mean sorting the hash.
oh, I see. Oh, maybe I think there is a confusion between hash function, the digest, what we saw, and what hash we will see here, right?
Yeah.
We will discuss that further,
Okay.
right? So when we cover that, maybe it will be clear, right?
Okay.
Okay, so I think I will increase the pace now. Okay, I will increase the pace because we need to cover a lot of ideas. Arbitrary size k. Okay, so what is a hash table? It's just an array, right? It's just an array. And all these are the hash values, and we store some information, right, beside all these hash values. And what can be the input? Input can be anything. As I said, anything. It can be a document, it can be an image, it can be a YouTube video, it can be a music, right? A song, some waves, some signals. It can be a number, it can be a floating point, anything. You know that any information is just a string, right? Any information, any data can be encoded as a string, right? For most practical purposes, all the data, right, that we communicate can be encoded as a string. That string is the input. You apply the hash function, right, on that key. We call this key. You get h of key or h of k. That's the hash function, right? That's the hash value. That's the hash value, h of k. What is h of k? H of k is the index in the hash table. And beside that index, you can store whatever you want. Maybe key value pair, maybe key this, k, and some value. It can be any record or a YouTube video, whatever, right? You store it. So you're not just storing h of k, you're also storing k comma v, right? Key value pairs. Got it? Fine. Now the table size we said is n here. Who decides this? You decide it, right? Whoever created that hash table, they decide what should be the value of this hash table or array size. That depends, right? If you're using a phone that is not a smartphone, maybe you pick a small value of n, right? If you're using a calculator and probably you want to use a hash function, maybe you pick a much smaller value, so on. Okay, so this is the core idea. Fine. So this hash function is a mapping from arbitrary objects. When I say arbitrary objects, it can be literally anything, right? It can be a car also. The description of the car is a string. That string will be added here as input to the set of indices 0 to n minus 1. This is the set 0 to n minus 1. So the key value pair k comma v is stored at a of h of, this is the index. This is a of h of k, right? As I said, this is an array. Hash table is an array. Let's call it a. All these are indices. All these are array values. Okay. Next. There are a lot of questions here. Some of them we will answer, some of them we will not. Okay. So keep thinking about these later. So how can keys of arbitrary objects be mapped to array indices that are whole numbers? See, these are arbitrary objects. We are mapping them to whole numbers. What are whole numbers? 0, 1, 2, so on. So the first idea is, the best way to proceed is first convert them into strings, right? And using encoding. There are a lot of encoding algorithms, convert them into strings. Once you have a string itself is a number, right? A string is a collection of bits. Any number can be converted into a string. Any string can be converted into a number, right? I mean, if you're dealing with numbers or strings, you can always mutually convert this, right? So because a string is a collection of bits, those collection of bits can be considered as a normal string, or it can be considered as a number, right? See, all this is interchangeable, right? This information is beautiful, right? Any string can be converted into a number and vice versa using the concept of bits. Okay, next. So for simplicity, we will divide the hash function into two stages or two parts, right? In the first stage, we map the keys to all these whole numbers. I mean, sorry, all these integers. Okay. In the second stage, we use this compression. And remember, hash function is a mapping from key to an index, right? Finally, this will be the index of the array, right? So we are trying to find that index. So in stage one is getting the hash code, convert them into integers. And in the second stage, use compression and convert these into 0 to n-1 for some fixed n. Okay. Now let's see how do we perform stage one, then how do we perform stage two. So there are a lot of ideas and algorithms for performing stage one, that is converting any input into integers. See, one simple idea is, see, if your data itself is byte or short or character, just upscale it to 32-bit int, right? We can use 32-bit int as our integer, right? Okay, so next, if it is float is 32-bit, and convert those into 32-bit integer. Similarly, double to 32-bit integer. And suppose this is a sequence of characters, x0, x1 to xn-1. So these characters, maybe there are ASCII values associated with them or some other values, right? It can be ASCII, or I mean, there are different types of encoding for characters. So use them, and maybe you can take a sum, or maybe you can use exclusive or many of the other, probably infinite number of functions that you can use on top of these characters to get a final integer, right? But these are some of the normal ones. The most important stage one hash code idea that we will use, and everyone uses, all your programming language uses, is this polynomial hash codes. So what is a polynomial hash code? Suppose these are n characters that are the input. What do? For every character, there is an encoding, right? Using ASCII or some other value, or some other encoding scheme. Use that character and apply a polynomial. So what is the polynomial here? It uses a and it uses n. What is this n? N directly comes from the length of the string here, right? Length of the string. What about a? You need to choose a. Maybe a is a prime number. Maybe it is, say, 137. Or maybe it is, say, 37. Something like that. I think Java uses a is equal to 37 or something like that, right? Verify. Because in every version, they might, change all these numbers. Say they do a lot of experiments. They try which hash code is giving, much better result. That means less collisions and all. And they change all these values. And typically they will be prime numbers. And which prime number is, again, it's more of an experimental question. They need to do a lot of experiments and try to choose the best value, right? So I think in one version, probably the latest version used 37 or something like that, right? You need to verify. And almost all your programming languages will make use of polynomial hash codes. And this is how they convert any string into a specific number. Make sense? Okay. So check the programming language details to find all these exact numbers. Anyway, so there is another idea here, cyclic shift hash codes. I mean, we will not worry about this. We will skip this. Next. So that is stage one. What is stage two? You convert these integers. Integers can be negative and positive, right? You need to convert these integers into indices from 0 to n minus 1. See, one simplest approach that we will use is the division method, right? You can just take I% n, right? Whatever is the value you get, integer percent n. It gives you a value from 0 to n minus 1. Okay, so I will leave out the other details. You can go through that. So here is a simple example. I mean, you can implement English dictionary using the hash table. I mean, you could also implement the English dictionary using a balance tree. But when you implement this English dictionary using different data structures, so hash table might give you better result, right? Because it is much faster than balanced trees. But of course, these are not the only data structures. You can use a wide variety of data structures. But why is it faster? Because of constant time, right? For searching, inserting, deleting, if you choose a good hash function. So this is the idea, right? You have word, comma, meaning. In the English dictionary, you apply a hash function to the word because word is the key, right? This is the key. This is the value. Okay, you get h of word. Suppose there are 500,000 words, right? So create a hash table of, 0 to 500,000 minus 1. And you get h of this word. So that will be the index. And which h do you use? Use a polynomial hash code, right? By default, Java has it. You can use the Java hash function itself. And here you will store the word and meaning. That's it. Okay, next. So let's talk about collisions. We said that when the input size is more, the size of all inputs, the word of all inputs is bigger than the word of all outputs here, right? So this word is bigger, the input word is bigger than the output word. Then due to pigeonhole principle, there will be collisions. So that means if you give K1, V1 and K2, V2, these are two key value pairs, H of K1 and H of K2, the hashed values of these might collide. They might collide. I mean, here K1 not equal to K2, but H of K1 is equal to H of K2. When they collide, right, what happens? What do you store here? Do you store K1 V1 or do you store K2 V2 or do you store both? Okay, so even if you store both, I mean, how do you resolve all these collisions, right? So we will see. There are a couple of schemes, ideas, right? Techniques to handle these collisions. So these are called collision handling schemes or collision resolution strategies. There are two major schemes, separate chaining and open addressing. So separate chaining is a good scheme if you have a lot of extra space. Why? Because it takes more space to create other data structures, secondary data structures, that those secondary data structures can be a list, can be a balanced search tree, or whatever. So, I mean, what is the primary data structure here? It is an array, right? You know that hash table is nothing but an array. So this is the primary data structure. So this separate chaining uses secondary data structures. That means it can use a list. So this can be a list, right? Or it can use a balanced search tree, right? It can use a balanced search tree. So each of this will lead to a balanced search tree. Okay, so if you have more space, extra space, you can think about using separate chaining. The implementation will be simple. Suppose you don't have extra space. You don't have extra space for all these secondary data structures. What you can do is you can use a more complicated idea. You will reuse the space in the hash table itself, the given hash table, given array, but the logic is more complicated to implement and analyze and so on. But then why do we care for this complicated logic? And think about this. There are a lot of devices where space is an issue. It can be a calculator, it can be tiny phones, right? Or even some phones, I mean, smartphones definitely have lesser space compared to laptops, right? Again, among smartphones, there will be a lot of space constrained phones, right? The space itself will be much smaller. Then maybe you can think about open address. Okay. Let's see. The first scheme we will cover is separate chaining. So separate chaining is a dead simple idea. So what is the idea here? Look at this. Each bucket A of j stores its own secondary container. So you know that hash table is nothing but an array, right? So each value here or each cell in this hash table or array will lead to another secondary data structure. That can be a list or a balanced search tree. For simplicity, we will assume that it is a list, right? And we will also give some pseudocodes based on this list. Okay, so this is your separate chaining. What is the logic? The logic is here. Suppose you want to do put of key comma value. So these are the three operations, right? You are inserting, you are getting a value, right? I mean, or you can say searching for the value, or you want to delete. Insert, search, delete. So we call it as put, get, remove. Okay, now let's see. For all these three functions, the first thing you need to do is you need to hash the key. You should always hash the key. That is the first logic, for all these three functions. What do you get? You get an index. Let's call that index as hash, right? Like once you get the hashed, you get the hash. That hash itself is the index of the table or array. Now, what do? A of hash is your array, right? Or array entry. And if that array entry itself is a secondary data structure, what do you need to do? Suppose that is a list. Add that key value pair in that list at the end, right? So in insert, you add that key value pair at the end of that list at the location A of hash. What about get? Get is also simple. You have the entry, you know the exact entry of the array, get of that key. So next, remove key. That means you will need to scan that list, right? So here also you will need to scan that list for searching for that key, scan that secondary data structure list to remove the key. So that logic is not shown here. So get means it gets the value, right? That means you're returning the value for that key comma value pair, but you're only given the key. You want to return the value, right? Okay, you need to traverse that entire list. So here you need to traverse that entire list and delete or remove. Okay, But the first logic is finding the hash. Now let's look at open addressing. Open addressing is complicated. Okay, so open addressing is complicated. We are not allowed to use secondary data structures. We are given a table. We are given an array. We have to make use of the same array, the same table, and try to incorporate, all these values there itself. Now the logic becomes more complicated. Okay, so just remember this. We will explain this using an example. We will cover linear probing and we will cover quadratic probing. Okay, you don't need to worry about double hashing or random number generator and so on. Random generator and so on. So the idea is you hash the key that gives you an index, check that index. If it doesn't work, then add f of I. What is f of I? So the first time you are adding, okay, so f of I is different for different schemes here. I mean, everything is open addressing. In open addressing, you can use different ideas for f of I. It can be linear probing, quadratic probing, so on. If you change f of I like this, right, you get different schemes. So let's try to understand linear probing using an example. So we need to look at what all these three.
Professor, you're muted.
Sorry. Okay, so let's start with the put function here. Our hash function is very simple. Key %10, right? Key %10. So if it is key %10 and if we are putting a value, what happens? Let's see. Initially, our array is empty and the array is of size 10, right? 10. And if you look at the hash function key %10, that 10 represents this hash table size. And okay, now let's do all these inserts one by one and let's see how the hash table changes. Suppose we are inserting 18. What is 18% 10 or 18 mod 10? It is 8, right? Go to index 8 and add 18. Fine, that's it, right? Now 18 takes the position of 8 index. Next, let's insert or put 41. 41% 10 is 1. So here percent means mod function, right? 41 mod 10 is 1. So we go to the index 1 and insert 41. Simple, very simple. Now we are inserting 22. 22 mod 10 is 2. We go to 2 and insert 22. Next 32. 32 mod 10 is 2. Now we go to 2 and we see that there is a value in 2, right? So this is a fail. So we do one probe. Probe is checking whether that cell is empty or not. If it is occupied, what do? We cannot store the 32 at the location 2, right? What do? We go to the next cell. See, in linear probing, what do? Plus f of I, right? Hash plus f of I, where f of I is I. So that means we are doing plus I. So plus 0 failed here. So we will do plus 1. Plus 1. So we insert 32 at 3 and we are done. So how many probes were required to insert 32? 2 probes. we had to check index 2 and we had to check index 3, 2 probes. And now we are done. Suppose we want to insert 98. 98 mod 10 is 8. So we check 8. Oops, 8 is already occupied. Then we add 1. We go to 9. 9 is free. Okay, we insert 98 at 9. 2 probes, right? Okay, next 58. Let's see 58. 58 mod 10 is 8. 8 is occupied. We go to 9. 9 is occupied. Then we go to 0. 0 is unoccupied and 58 goes to 0. 3 probes. Right? And try this. Suppose you want to insert 78. What happens? 78 mod 10 is 8. 8 is occupied. 9 is occupied. 0 is occupied. 1 is occupied. 2 is occupied. 3 is occupied. 78 goes here. So how many probes? Count this, right? So this is your insert logic in linear probing for open addressing. Now let's look at the remove logic. Remove logic is more complicated. It's not simple. Okay, let's see. Suppose our hash table is like this. Okay. Suppose we want to delete 58. What do we do? 58 mod 10 is what? 8. We check 8. We have 18 here. 18 is not same as 58. So move to next cell. Check 9. 98 is not same as 58. Check next cell. 0. Okay. So 58 is same as 58. This is success, right? So we delete 58 and this became an empty cell. Right? Empty cell. Okay. Now suppose we are deleting 19. What happens here? 19 mod 10 is 9. 19 is not here at 9. We encountered an empty cell. Our scan ends whenever we hit an empty cell, right? We shouldn't proceed after empty cells. We stop at empty cells. So we think that 19 does not exist because we stopped at empty cells. That's incorrect, right? Because 19 really exists in the hash table. So what's the problem? The problem is our logic of remove itself is not a good logic. So whenever you find that number, we shouldn't delete it and make it an empty cell. That was our faulty logic. So this is not a good idea for remove, right? So what else we can do? We can think about a new idea. Instead of, whenever we find that cell, instead of replacing that cell with empty cell or completely deleting it, what we will do is we will identify it as a kind of a dead cell or a defunct object, right? Let's apply that logic here. Let's look at this. 58. So 58, you check 8, 9, and 0. You found 58. Instead of deleting it, what you do is you mark it as defunct. See, the cell color has been changed. You mark it as defunct. Okay, next you go to 19. Keep searching for 19. 19 mod 10 is 9. So search here, 98, 58, 41, 22, 32, 78, 19. You found it, right? So like once you found, again, do not delete it, just mark it as defunct. right? What is the idea here? Whenever you want to delete it, do not delete that number and making that cell null or empty. Just label or mark that cell as defunct object and continue the search. And this is important, right? This is a beautiful idea, simple idea, but it works beautifully.
Question, Professor.
Yes.
So if that's the case, then you cannot make reuse of those.
No,
entries,
you
right?
can. So then we will change the put slightly, right?
Okay.
How? So whenever you find an empty cell, insert it, or if you find a defunct object, rewrite it.
Okay, gotcha.
Got it?
Thank you.
So yeah, we need to slightly change put again. I mean, modify put again, right? Then you can reuse all these defunct objects. But just that while deleting, we are not deleting them and considering them as empty cells. That's the only difference. But now this works, right? So here is the logic. It might seem complicated. It is not, right? So the idea is for all three functions, you have to hash it first. Okay, I mean, this by default has it. So hash the key, you get the index. So what you do is I value is 0, right? You keep checking hash plus 0, hash plus 1, hash plus 2, so on in that cyclic manner until you hit a null. Okay, so if you have scanned all the objects in the table and did not find any empty cell, that means the table is full. You cannot insert another item. Suppose you were able to find an empty cell, then insert that key comma value pair. That's it. So here is the actual insert. What about get? Get has a very similar logic as put, right? So verify that. I mean, okay, verify this, right? It has a very similar logic as put. What about remove? So remove is find slot for removal. So here I have not shown the entire code because it's more complicated, right? With the defunct and all that. So assume that you find the slot for removal. Okay, so oh no. So finding slot is just same as this getting, right? It's very similar to this getting. So I have not rewritten all that code here. That is simple, right? You can replace it with the exact code. You get the index, right? Now what do? Let's see. So if that index is less than 0, return null. Okay. If the value is a of index dot value, a of index is defunct. Why? See, we are not deleting that cell and making it an empty cell. We are just calling that as a defunct object, right? Okay, then n is equal to the number of entries, right, that are inside the hash table is represented by n, right? N is equal to n minus 1, and you can return the value. But again, so here what I have not shown is how to use defunct in the put logic, right? That can be adapted, but because it makes the code a bit more complicated, I have not added it, but you can reuse all these defunct objects also in the put. Make sense?
Professor.
Yes.
I get the point of you might not have space for this, but you have a problem with this in that the array could be full, where if you do chaining, you never have that problem.
Right. True.
Is that right? Okay.
True. So for that reason, so what we suggest is something like this. So we define something called load factor. The number of entries in the hash table divided by capacity of the hash table, right? The load factor should always be kept as less than 1. If the load factor is equal to 1 or greater than 1, you need to rehash it. Remember how we created bigger arrays in dynamic arrays, right? Similarly, we need to use the same idea. So there we used to create a bigger array and copy the elements. So here also, if any time lambda is greater than 1, you want to create a bigger array and rehash all the existing elements and throw away the existing, previous hash table. Same problem exists here also. Okay, so from experimentation, what the authors have found out is that if you're using separate chaining, so try to maintain lambda, this load factor, as less than 75%. If you're using open addressing, make sure that the load factor is less than 50%. Okay, so if you are using a good hash function, see, the focus is more on the good hash function, then the assumption is that, there is rigorous analysis here. We will not cover it. It is out of scope, right? So that shows that the number of collisions will be minimal, and hence hence there won't be a lot of collisions. That makes sure that put, get, and remove function will have O of 1 expected time. And where do we have this rigorous analysis? It is the analysis of a good hash function. And how do you define good hash function? How do you prove it? All that analysis, right, is out of scope, right? We will not cover those rigorous probabilistic analysis. Make sense? So applications, okay, I don't need to cover this, but you got the idea, right? Now, next, how is quadratic probing different from linear probing? See, here you used to do hash of key plus I, right? In linear probing, you need to do hash of key plus I squared in quadratic probing. That means, so here in linear probing, you used to do hash of key plus 1, hash of key plus 2, hash of key plus 3, right? But here you need to do hash of key plus 1, hash of key plus 4, hash of key plus 9, hash of key plus 16, so on. You got it, right? The simple rule is that, see, if you do linear probing, all the items, whenever you are inserting, they will be grouped together, right? They will make clumps or groups, and a lot of probes happen around this point. To avoid this, quadratic probing was created. See, with 32, 32 is fine here. Suppose if you had 3 probes, right? 58. Okay, you check 18, then you check this position, right? 9 position, and then you do 8 plus 1, and 8 plus 4 mod 10. What is 8 plus 4 mod 10?
2.
2 directly, right? Without looking at some of these entries. So it is said that that gives a bit better results than linear probing because that avoids clumps. Again, we will not see all that theoretical analysis or experimental analysis, right? We will just assume it. Okay. And what kind of questions can be asked? I can give you a series of numbers. You want to insert them or delete them, right? Either using linear probing or separate chaining or quadratic probing, so on.
Professor, with quadratic, I understand you're going to have less clumping, but you're going to have to be aware that you could have like something put in index 5 that has null values before it and after it. So when you're looking for it, you have to be aware that that could happen, right?
Correct, true.
Okay. Is that, okay, it's, okay,
So because this hash function is deterministic, right? Whether you are putting, getting, deleting, right? You go through the exact same steps. So that there is no problem later, right? You will have to go through these exact deterministic steps. Okay, fine. So we will stop here. That is the end of hash tables. In the next session, we will cover heaps. Okay.